Okay, semiconductor detectors are next. We have an interesting, I think, and very relevant chapter ahead. We'll have to discuss the operating principles of silicon when it is in reverse bias voltage with a large depletion zone. And we'll have to discuss the detector applications of such detectors, which are typical thicknesses of hundreds of microns. And at the end, we will discuss their main application in, for example, hadron physics collider experiments. The tracking detectors will discuss what spectrometer measurements are. As usual, a list of references that provide plenty of extra information. Of course, I can only scratch the surface. Anyway, let's talk about semiconductor detectors. Where are semiconductor detectors used? They are used everywhere. Nuclear physics. They can be used for energy measurements of charged particles directly in the MeV range. One can also do gamma spectroscopy for not too high energies and obtain a precision determination of the photon energy. We're going to see examples of that. In particle physics, that's our business, they are used for tracking and for vertex detectors, which are, their task is a precise determination of the particle tracks as they bend in the magnetic fields, and to reconstruct the decay vertices should such a displaced decays take place. Now, recently, in the last years, silicon detectors are also increasingly used for calorimetry. For example, the high luminosity upgrade for the CMS detector will feature a highly segmented silicon calorimetry in the end cap, the so-called HG curl. This will allow to resolve the decays, the individual decays in the jet as its particles shower and propagate through the silicon detector. They are also used in satellite experiments because after careful design, no large currents are needed, and there are many other industrial applications in security, medicine, and biology. There are advantages and disadvantages to semiconductor detectors. One first example is semiconductors have a high density, and hence there is a high ionization yield per unit length. It also means there's a large energy loss in short distance. That's good for recording the signal. If the detector is thin, that's bad because there are large Landau fluctuations. Diffusion is smaller than in gases because of the higher densities, which means that the position resolution can be as good as 10 and even better, tens of microns. The ionization energy is only a few electron volts. We've seen for argon it was 26 electron volts, not counting secondary ionization. It was even 90. Here we talk about only a few electron volts, a single number like 1 to 6 or so per electron hole pair, compared to the gasers and the scintillators are even use even higher ionization energy. Of course, one has to keep in mind what we are doing here. So for low ionization, for these silicon trackers with the low ionization energy, we want to do tracking, so we don't want to disturb the particle. Similarly, in gas detectors, here we have a compromise, but with these gases, we operate large volumes. With scintillators, we want to stop the particle. So of course, the ionization energy is okay when it is higher, because anyway, the particles we want to detect shower and stop, and so a keV or so is not a problem. One of the biggest advantages is that semiconductors are used in industry in microchip technology, and there's plenty of money behind that, and therefore the hardware groups at the institutes work together directly with the companies in one-on-one exchange. They easily therefore integrate with the readout electronics, which are often mounted in one go with the sensor, or assembled with wire bonding or with other bonding steps, but identical materials are used. And silicon has a very high intrinsic radiation hardness. That's a very big advantage. Lead tungstate, for example, the electromagnetic CMS calorimetry is also radiation hard, but not as much, and hence at the areas that are closest to the beam pipe has already lost 95 to 96% of its initial light yield. So aging is important, and aging is better under control with high intrinsic radiation hardness, and that is the case for many semiconducting detectors. There are important disadvantages. There is no internal amplification. There is no avalanche formation in a semiconducting detector, usually at least. So the signals are small. And there's also fairly high cost per surface unit. It's because we're not talking about the silicon is cheap, but detector R&D and the production of the dedicated electronics and the printing of the micrometer wide structures is something that is a high investment. And while there is large experience in industry, there's very little companies working on semiconducting sensors, in particular for the relative large structures that we're dealing with here. We're dealing with large structures because of the radiation hardness. So we cannot directly use most of what the companies have learned in microchip technology, because there is no radiation concerns in a graphic card, for example, but there is in a particle physics detector. So there's only a few companies who can do that. Hamamatsu, Infineon, and so there's little competition, and we often rely on single vendors, and that can have undesirable consequences for our political leverage when we buy such things. So, long story needs to end. We talk about the operation principle now of a semiconducting detector, in particular for tracking applications. The semiconductors actually work as an ionization chamber. That's a shortcut for no amplification. The challenge in designing a semiconductor is to find the best interplay of the material, the sensor geometry, the supply and the readouts, and then the cooling and the detector geometry. All these have highly non-trivial interplays. I show you two very different solutions to a similar problem. The problem is tracking. The top image is the CMS tracker, which has a surface, a silicon surface, a sensitive area of 200 square meters. So there's 200 square meters of of instrumented silicon. So that's a digital camera with a 200 square meter sensor operated at 40 megahertz. So still by today's standard is a rather bizarre and extreme detector. It was partially developed at our institute in Vienna, and so the sensors were designed, and we also partially built the sensor modules that you can see here. They come in several layers. Another important detector that was developed at our institute is the BEL2 secondary vertex detector with a sensitive area of 1.13 square meter. It is 80 centimeters long. That is a rendering here, but it has been built meanwhile and installed in the BEL2 detector. So silicon is the material of choice for most semiconductors because it is comparably cheap, easy to handle, and we have the most experience with it. It has a moderate band gap between the valence and the conduction band of 1.12 electron volts. The minimum energy to create an electron hole pair is only 3.6 electron volts. That's very low compared to gases that are used in ionization chambers. We talk about 15 to 25 electron volts for an electron ion pair on average. So 3.6 is an order of magnitude less. In other words, it's not difficult for a particle to create an electron hole pair. We have a high density and a high atomic number according to Peter Bloch principle gives a high ionization yield. So we have, as the particle traverses the detector, that the EDX is high, there's a high specific energy loss, and we can make the detectors thin. If we make them thin, the lambda fluctuations become important. If we want to remove the lambda fluctuations, either we make the sensors thicker so that the distribution becomes more Gaussian, or we make more layers. It's very important, next point, that the carrier mobility, so the electrons and the holes. So here we don't have ions in contrast to a gas detector. We have an electron and we have a hole is very high and allows to collect the entire signal within 30 or so nanoseconds. So silicon detectors are very fast. Moreover, in gaseous detectors, when we create an electron-ion pair, the electron moves fast and the ion moves slow. In semiconductors, we create an electron-hole pair. We lift one electron from the valence to the conduction band, and the hole and the electron have similar dynamical properties. They don't have the same properties. The effective mass is different, sometimes sizably different, but only 20, 40, 60% in that regime, and not the factor of 100 that we had for electrons and ions. After all, a hole is just an electron missing. Okay, and I've said a few times the industrial fabrication techniques are something that we benefit from. For example, there's a high experience in using silicon oxide, which is an excellent dielectric that's routinely used in the production of such sensors. Let us now talk about the main objective of tracking detectors. I've mentioned calorimetry, but I want to stick for this lecture with the use case of tracking. The objective is to measure the particles' track without disturbing them. So for example that we already had, we have a jet it consists of particles. Some of these particles may be long-lived. So like here we may have a secondary vertex from a B meson, and we want to measure the particles track with a high accuracy and reconstruct maybe these secondary vertices. Now, to determine the positions of the primary vertex and the secondary vertices, one needs the best position resolution that's in any way achievable. So that's the dominating goal for tracking. Therefore, the detectors must be highly segmented. Close to the beam pipe, we need pixels. A little bit away from the beam pipe, we can tolerate strips, but we need to have the strips in different angles so that we can get more, so that we have less ambiguities in the geometric reconstruction. Now, the driving force is therefore the position resolution and the achievable segmentation. The achievable segmentation is only limited by the size of the signal. Of course, we have to amplify the ionization signal. It is not intrinsically amplified. And that's one limiting factor. So the segmentation is limited by the size of the signal. And once that is achieved, we move it as close as possible to the interaction point. That means it has to be, it will have a given radiation hardness, and then we move it as close as possible to the interaction point. We talk about a few centimeters away from the interaction vertex, where the first pixel measurements actually happen. With few centimeters distance, 5 centimeters, and tens of microns position resolution, we can achieve 10 to 100 micron primary and secondary vertex resolution measurements, and with these we can identify, for example, the B meson. And that's really important to gain information about the third generation of elementary particles. There are of course, there are other use cases, but this is what we think of. The other one of the most important other use cases is the spectrometer measurement, which is the measurement of particles track and inferring the momentum. That is we will discuss this in detail in chapter 4. We'll derive this simple formula. Imagine this part of this circular track here that I trace out with the mouse cursor is the path of a charged particle. Now, you need to measure the curvature radius. You know where the track starts, you know where it ends, and the curvature is given by this little s, which is called the sagitta. Now, the resolution in this measurement, the sigma s, the resolution of the sagitta, we will derive that it immediately determines the momentum resolution. So the relative resolution in the sagitta to the relative immediately determines the relative resolution in the momentum. And typical lengths are several meters. We have the pixel, for example, we have a pixel detector here, then we have a tracking detector here, then come the calorimetry, the magnet, and then starts hopefully the muon system. And over the whole diameter of the detector, which can be several meters, we can thus measure a muon track and reconstruct its momentum. And if we do it well, we get a percent level momentum resolution up to the TeV scale, and that allows us to measure to test even physics beyond the standard model in the TeV regime and whatnot. In summary, it's important that we get our silicon detectors functioning close to the beam pipe with high occupancy and with high accuracy, so that we can have a high precision measurement of the curvature of the track, because that's what drives the momentum resolution. More of that next time. Now we move on. And look at some pictures. The event to the left is taken from CMS. In the middle, the event in the middle is taken from the Atlas experiment. You nicely see the primary vertex and two decay vertices. The pixel and strip detectors in these large collider experiments are often onion shaped. So unfortunately, you cannot see my hands now. I'm trying to make it. I'm trying to make an onion. That means if in the, let me try to describe it. For the CMS event to the left, this is best seen here. In the transverse plane, we have here in red the projection of the different tracking modules. There are up to 6 layers behind each other, and if you imagine this in the RC plane, the cylinder is ended with end caps of modules on both sides, so that we have an onion layered structure. The secondary vertices, let's look at an example. One third generation lepton is the tau lepton. The tau lepton from a Z boson, let's say. Let's say a Z boson is produced at rest. The Z boson is 91 GeV. That means if it's produced at rest, it decays to 2 tau leptons. It has 45 GeV. So we have a tau lepton with a momentum of 45 GeV. Now at rest, the C tau of the tau lepton, so the lifetime of the tau lepton in its rest frame, multiplied with the speed of light, is 87 microns. Now multiplied with the beta gamma of multiplied with the, I'm sorry, I misspoke before. Let me start over. The beta gamma of the tau lepton is the 45 GeV from the half of the Z boson that got converted into the tau lepton's momentum, divided by the tau lepton's mass, which is 1.78 GeV, gives a factor in the vicinity of 30, between 20 and 30. So the beta gamma C tau is 2.2 millimeter. Beta gamma C tau is the average distance a tau lepton with a momentum of 45 GeV will travel. So we have 2.2 millimeters, and we have 100 tends to 100 or so micrometer impact parameter resolution, as you know, and as we've discussed, the impact parameter is the distance of closest approach when the track is extrapolated to through the detector and then compared to the primary vertex. So the secondary vertices can then be reconstructed with a very small arrow ellipse, and the tau leptons can be identified with very high efficiency. So these are the main applications brought to reality, if you want. Now we talk about the physics of the detector. What types of semiconductors are there? There are elementary semiconductors and there are compound semiconductors. We'll not discuss many of these applications. Most of these are useful only for special purpose electronics not used in colliders. But nevertheless, let me give you some details. Germanium is used in nuclear physics and also in searches for dark matter. It needs to be cooled because it has a very small band gap of 0.6 electron volts, which means its thermal behavior is not satisfactory at room temperature. You need to cool germanium. Silicon is the main material used for high energy physics detectors. It can be operated at room temperature. Listed the advantages, synergies with the electronics industry. It is definitely the standard material for vertexing and tracking. There's also diamond. Diamond either from a single crystal or from chemical vapor deposition, which is a chemical way of producing artificial diamonds. Diamond, as you know, is an allotrope of carbon. Allotrope is a word for same thing, but with a different crystal structure. Diamond has a large band gap of 6 electron volts. It requires no depletion zone, as we're going to see. That means much less necessity for the electronics that are needed for operating the detector, and it's extremely radiation hard. Now, the disadvantage of diamond is that the signal is low and the cost is very high. So unless, I don't know, the Queen donates her crown jewels to our next particle collider, I don't see diamonds being used. But there are important applications for diamonds in small scale experiments. But the biggest set of applications is most definitely covered by silicon, not also vertexing and tracking, now also increasingly for calorimetry. Then you should know at least that there are compound semiconductors. These have 2 or more atomic elements. One is therefore much more flexible for the electronic and chemical composition, and one can play around with type 4, type 3, 5, and type 2 is 6 compounds where these numbers correspond to the column in the periodic system. All these materials have different atomic numbers and will therefore have very different behavior as very different TEDX. And so special purpose detectors can be built by tuning the semiconductor to the desired property of the detector. Important compound semiconductors are gallium arsen, which is even faster than silicon. It's also probably more radiation resistant. Not so much is known about it. There's certainly less experience with this material in industry, and therefore it costs more. Other important semiconductors are cadmium tellure with very high C, hence is very efficient to detect photons. Always remember, if you want to detect highly energetic photons, the means by doing that in an ionization detector is the pair production in close to the nucleus, which is proportional to C squared. Okay, gallium arsenide, I think, is used in light emitting diodes. So let's look at the crystal structure of semiconductors, just so that you know. Cilium and germanium and diamond are in the diamond lattice. these group 4 elements. The diamond lattice is 2 face-centered cubic lattices, where at each of the 2 face-centered cubic lattices intersection points, we have an atom sitting. The 2 lattices are shifted by 1/4 along the diagonal of the cube. So each atom is surrounded by 4 equidistant neighbors, and the lattice spacing is very dense with a parameter of 5 angstrom for silicon. Most of the compound semiconductors come in the zinc blende lattice. In fact, this is the same lattice. However, on each sublattice, you have one of the compounds sitting. So globally, it is the same lattice, but each sublattice consists of, each sublattice is occupied by one of the compounds. Gallium arsen is a direct semiconductor. That is special. Direct means that the creation of an electron-hole pair needs no energy transfer to the lattice, because electrons and holes have slightly different dynamics in most semiconductors. Because the effective mass is different. It's because the energy levels they operate in are, of course, different, and hence, if you create an electron-hole pair, you have to transfer a small momentum to the lattice, and that gives you directional dependent effects, because the dispersion relation of an electron and a hole is first of all different in such a lattice, and it's also dependent on the direction. So a small amount of energy always needs to be transferred, except for gallium arsen, where this is not needed, and the efficiency of creating electron-hole pairs is therefore much higher, and that's exploited in the light-emitting diodes. That's as much as I want to say about direct and indirect semiconductors. We will only deal with indirect semiconductors. We look at silicon here. Silicon at temperature 0 has 4 closest neighbors, and the 4 electrons in the outer shell are shared and form covalent bonds with the neighbors. At the low temperatures, this is an insulator. All electrons are bound. All of them are valence electron. For finite temperatures, the thermal vibrations, they break some of these bonds and they free some of the electrons. So electrons can move around and cause conductivity. That's the electron contribution to the conduction. There are now holes, and into these holes, the neighboring electrons can jump. And hence the dynamics of the holes and the dynamics of the electrons themselves is rather similar. There's therefore also hole conduction, because also the hole acts as an effective particle, can change position, and hence contribute to the conduction. That's what we call the hole conduction. The dynamics between electrons and holes somewhat differs because, as I've discussed in a little bit of detail, the different interactions with the lattice, with the surrounding atoms, is different, of course, for electrons and holes. It's almost 3. We do not discuss energy bands. It's an ideal moment to stop, because next time we start with the basics. With semiconductors, we compare isolators, semiconductors at 0 and at finite temperatures, and metals. We will do a very simple account of the number density of electrons as a function of the energy. We'll discuss briefly the gap structure, and then we'll talk about drift velocity, resistivity, the mean free path of the electron-hole pairs in the semiconductor. As usual, we'll compare materials, and then we'll construct the detector. And that will be the topic of next time. I stop here. I stop the recording, and you are free to ask questions in case you want.